Okay, this is the third video in electric fields. What we're looking at here is creating a... Okay, what we're going to do here is set up a electric field. To do that, we need to have these parallel plates. Now, to understand more about what these parallel plates do, you could think about how we set one up. We have these two metal plates, they're just pieces of metal. And if we connect it to a cell, then you can create a charged plates. This plate down here will have more electrons. Okay, so that's going to be the negative plate. This one up here will have too few, so this will be the positive plate. So, let's have a look at what charges do when they are fired between charged plates. Okay, so if we have this top one here, if that is a positive plate, in other words too few electrons, this one down here is a negative plate, then you can create an electric field. Now if I send in an electron flying into there, or let's say a proton, then from the law of charges we know that the electron is going to be attracted to the positive plate, so it's going to curve upwards, and the proton is attracted to the negative plate, so it will curve downwards. Okay, let's see, we want to look at the work done by moving an electron in an electric field. So this electron here, this one here, will quite happily move this way, okay? Because remember, the electric field shows the way a positive charge would go. In this case, if it was a positive charge, it will head along the direction of the arrows. However, this is a negative charge, so it would want to go this way. Okay, so if I want to grab this charge and move it from point A to point B, which is a distance x, then I would have to do some work against the field. So remember what work is. Work equals force times the distance we're going to move, which in this case is x. Okay, and now let's look at what the force do. So work equals force times x, and we know already that force is equal to EQ. Okay, the electric field strength multiplied by the size of the charge there. In this case it's an electron. So let's substitute this term for force into there for that one, and you then get work equals E times Q times X. And then we have just derived a new formula for work done in an electric field. Sometimes you can write like this. Okay, so this case here we've got two plates, and we have an electron sitting here at the negative plate, the positive plate. And what we're going to do is we're going to move it to this side here. Okay. Now, if we say that the distance is going to move is equal to 10 centimeters. Then we can work out A, how much work is done against done when an electron is moved against an electric field of strength 30 newtons per coulomb. So the answer, so A, okay, work equals EQD. Okay, what's the size of E? It was 30. I'm going to multiply that by Q, which is actually 1.6 times 10 to the minus 19 coulombs for an electron. And we're going to multiply that by 0.1 meters. And then you'll find the work done. Now B is asking us, we've got the electron to go against the field to here, so we've pushed it, okay, well, push it against the way it wants to go, so this must be a negative there, positive on that side. Okay, now if we release it, it's going to want to accelerate coming back. Okay, well, how much energy is going to gain? If it's got zero energy there, or sorry, it's got a certain amount of potential energy there, it's going to gain a certain amount of kinetic energy there. Okay, so the work done will be equal to the kinetic energy when it gets back to the other plate. So all we've got to do is just make that answer from A equal to half mv squared and solve for V. Okay, potential difference, essentially this is voltage in electric field, is the work done per unit of charge when it is moved between 2 points in the electric field. Okay, so looking at this formula, voltage or potential difference is equal to the work done divided by the unit of charge. So just to give you an idea of this, if I had a couple of plates, okay, and the voltage between them was 1 volt. In other words, I had 1 volt here and 0 volts here. Then what's the work done in moving a charge of 1 coulomb from there to the other side? It would be equal to W equals VQ. Okay, so it'll be 1 times 1, which equals 1 joule of energy to move a 1 coulomb charge through 1 volt. Now what we can also do with this formula, let's have a look at it. So V equals W over Q. Okay. Now let's rearrange this. Okay, and put in some values that we already know. Okay. Now we know that work equals force times distance. So let's put that into the equation there. So V is equal to F times D divided by Q. Now you might see something quite interesting here. That's the F divided by Q. Okay, that's what we've looked at earlier. That is the formula for electric field strength, the defining formula. Okay, so let's put those values in. So, oh sorry, put this letter here in for F over Q, and then you get V equals E D. Okay, well let's rearrange this. We actually now have another formula for electric field strength. What are the units of this one? Well, what's V? V is volts, and what's D is meters, okay, because it's a distance, so it's volt per meter. Okay, so remember the defining formula for electric field strength equals F divided by Q, and the unit from that is going to be equal to newtons per coulomb. However, in this case, we've got another formula E equals V over D with the unit volts per meter. So for an example here, what we've got there, we've got a distance, we've got a voltage, E equals V over D. You just put it into the equation. Remember meters. Similar thing here, okay? However, probably a little bit trickier. Okay, so we've got two ways of doing this one. Let's do the hard way first. Okay, so what you could work out is the electric field strength. It looks obvious, you've got voltage and distance. So it'll be 100 divided by 0.2. Where's that from? That's from V over D. Okay. Now from that, you could then put this into an equation that relates work done. Okay, so work equals EQD that we've had earlier. Okay, so you could put in V divided by D multiplied by Q times D. Okay, oh, those D's cancel, and we just get VQ. Okay, so we could actually work out the work done for moving between the two plates, and then we know then that the work done is going to be equal to the kinetic energy, which is half mv squared. Another way, we did work out the electric field strength. So let's look at a more interesting way. Okay, so electric field strength, remember, was equal to V over D. What if we then use that for a force? So force equals EQ. Okay, so it's going to be equal to VQ over D. So that gives us the force. We could then find out the acceleration from F divided by M, from F equals MA. So we then can put in VQ over D divided by M to find the acceleration, and then use a kinematic, okay, which is probably a little bit longer way. This example here, I would like you to try in class. And post your answer.